Moving on, let's now examine 9-lead motors, of which there are two varieties, 9-lead Y configured motors and 9-lead delta configured motors. As applied by their titles, Ys are always Ys and you can't do anything about it. The same thing can be said about deltas. 9-lead motors, however, have the advantage of being applicable for dual voltage operation. Bottom line up front, low voltage configurations are associated with windings in parallel, whereas high voltage configurations are associated with windings in series. Allow me to demonstrate. Consider a 9-lead Y configured motor consisting of 6 windings, 3 independent and isolated with both ends accessible, and 3 permanently bonded together in a Y configuration with only one ending of each winding accessible. Windings 1, 4, 2, 5, and 3, 6 can be positioned as needed, whereas windings 7, 8, and 9 are a conjoined set of 3. In a low voltage configuration, 4, 5, and 6 are tied together, forming another Y. Then 1 is tied to 7, 2 to 8, and 3 to 9, forming an almost overlapping double Y in parallel with one another. Primary lines L1, L2, and L3 will be connected to conjoined terminals 1, 7, 2, 8, and 3, 9, where swapping any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, low voltage Y configurations are sometimes known as YY configurations. Given each winding is a balanced load, there is no need to join the center of the two Ys. It should be noted that parallel impedances add more paths for current. This is why the low voltage entry in a motor nameplate has twice the current as the high voltage configuration. A motor connection diagram illustrating a 9-lead Y configured motor set up in the low voltage configuration might look something like this, where L1 goes to 1 and 7, L2 goes to 2 and 8, and L3 goes to 3 and 9, and 4, 5, and 6 are tied together. In a high voltage configuration, 4 is tied to 7, 7 to 8, and 6 to 9, forming a large Y with each leg of the Y being a series combination of two windings. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, high voltage Y configurations are sometimes known as big Y configurations. It should be noted that series impedances add up. This is why the high voltage entry on a motor nameplate has half the current draw as a low voltage configuration. A motor connection diagram illustrating a 9-lead Y configured motor set up in the high voltage configuration might look something like this. L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, and 6 to 9. Similar things can be said about 9-lead delta configured motors. Low voltage configurations are associated with windings in parallel, whereas high voltage configurations are associated with windings in series. Allow me to demonstrate. Consider a 9-lead delta configured motor consisting of 3 sets of paired windings permanently joined together. Visualizing 9-lead deltas is a little difficult unless you just pick a direction and stick with it. In this case, let's go clockwise. Winding 9-1 is joined to windings 1-4 at corner 1. Winding 7-2 is joined to winding 2-5 at corner 2. And finally, winding 8-3 is joined to winding 3-6 at corner 3. You can see how each pair of conjoined windings in a 9-lead delta configured motor essentially forms two legs of a partial triangle. Terminals 9 and 4, 7 and 5, and 8 and 6 are ends, whereas terminals 1, 2, and 3 are the corners. In a low voltage delta configuration, one overlaps the two legs to form one triangle on top of another. Ends 6 and 7 are tied to corner 1. Ends 4 and 8 are tied to corner 2. And finally, ends 5 and 9 are tied to corner 3. Primary lines L1, L2, and L3 will be connected to conjoined terminals 617, 428, and 539. Where swapping in a two-applied phase sequences reverses rotational direction. For hopefully obvious reasons, low voltage delta configurations are sometimes known as delta-delta configurations. It should again be noted that parallel impedances add more paths for current. This is why the low voltage entry in a motor nameplate has twice the current as a high voltage configuration. A motor connection diagram illustrating a 9-lead delta configured motor set up in the low voltage configuration might look something like this, where L1 goes to 617, L2 goes to 428, L3 goes to 539. In a high voltage delta configuration, we don't overlap the two-legged triangles, but rather the ends of the partial triangles simply join hands. 4 is tied to 7, 5 to 8, and 6 to 9, forming a large delta, with each leg of the delta being a series combination of two windings. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping any two applied phase sequences reverses rotational direction. For hopefully obvious reasons, high voltage delta configurations are sometimes known as big delta configurations. Should again be noted that series impedances add up. This is why the high voltage entry on a motor nameplate has half the current draw as the low voltage configuration. A motor connection diagram illustrating a 9-lead delta configured motor set up in the high voltage configuration might look something like this. L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, and 6 to 9. Before we move on to examine 12-lead motors, allow me to discuss a feature unique to low voltage Y and delta configured motors. You note each leg in a low voltage Y or delta is a parallel arrangement of two windings. Parallel configurations draw more current because there are more paths for current flow. If somehow we remove one path, at least temporarily, less current will flow. Another type of reduced voltage starting method, called a part winding reduced voltage starter, takes advantage of this fact. Similar in nature to a Y-start delta run reduced voltage starter, a part winding reduced voltage starter has two defined stages, a start and a run stage designed to reduce inrush current and modify the starting torque of a motor under its direction. A part winding reduced voltage starter starts a low voltage configuration with only one set of windings, such that each large impedance path draws smaller inrush current. Then, after a predetermined time allowing the motor to accelerate, the second set of windings is brought in parallel, thus drawing more current. Here's an example of a part winding reduced voltage starter applicable for a low voltage Y configuration. We'll examine part winding reduced voltage starters in greater detail in later lectures. Let's now examine 12-lead motors, the most flexible of options. 12-lead motors are characterized by 6 individual isolated windings with both ends of each winding accessible. Winding 1-4, 2-5, 3-6, 7-10, 8-11, and 9-12. Given your understanding of the previous content, you'll no doubt see the utility of 12-lead motors and that they are truly customizable and can be configured as low voltage Ys, high voltage Ys, low voltage deltas, or high voltage deltas. As with 9-lead Y configured motors, one configures a 12-lead motor as a low voltage Y by making two small Ys by conjoining terminals 4, 5, and 6, and 10, 11, and 12. Then one overlaps the Ys in a parallel configuration by tying together leads 1, 7, 2, 8, and 3, 9. Primary lines L1, L2, and L3 would be connected to conjoined terminals 1, 7, 2, 8, and 3, 9, where swapping any two applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a low voltage Y is sometimes referred to as a YY configuration. A motor connection diagram illustrating a 12-lead motor set up for the low voltage Y configuration might look something like this. L1 goes to conjoined terminals 1, 7, L2 goes to 2 and 8, L3 goes 3 and 9, 4, 5, and 6 are tied together, as are 10, 11, and 12. Similarly, one configures a 12-lead motor as a high voltage Y by making a large Y by conjoining terminals 4 and 7, 5 and 8, and 3 and 9 to make 3 series branches. Then one joins leads 10, 11, and 12 in the center. Primary lines L1, L2, and L3 would be connected to terminals 1, 2, and 3, where swapping any two applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a high voltage Y is sometimes referred to as a big Y configuration. A motor connection diagram illustrating a 12-lead motor set up in the high voltage Y configuration might look something like this. L1 to 1, L2 to 2, L3 to 3, 4 to 7, 5 to 8, 6 to 9, and finally 10, 11, and 12 tied together. In order to configure a 12-lead motor as a low voltage delta, one would make two overlapping deltas by conjoining terminals 1, 7, 6, 12, 4, 10, 2, and 8, and 5, 11, 3, and 9. Primary lines L1, L2, and L3 would be connected to conjoined terminals 1, 7, 6, 12, 4, 10, 2, and 8, and 5, 11, 3, and 9, where swapping any two applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a low voltage delta is sometimes referred to as a delta-delta configuration. A motor connection diagram illustrating a 12-lead motor set up in the low voltage delta configuration might look something like this, where L1 is applied to 1, 12, 6, and 7, L2 is applied to 2, 10, 4, and 8, and L3 is applied to 3, 11, 5, and 9. You note the numerical arrangement of the terminals for a low voltage delta configuration is different than that of the previous Y configurations. As illustrated, 7, 8, and 9 is on top, and it goes 6, 4, 5, and 12, 10, 11 left to right. This prevents lines crossing each other in the diagram. You should note that not all manufacturers use this technique, so be prepared for variations on this theme. Lastly, one configures a 12-lead motor as a high voltage delta by making a large delta by conjoining terminals 4-7, 5-8, and 3-9, making 3 series legs. Then one joins leads 112, 210, and 311 as the corners. Primary lines L1, L2, and L3 will be connected to conjoined terminals 112, 210, and 311, where swapping any two applied phase sequences reverses rotational direction. Again, for hopefully obvious reasons, a high voltage delta is sometimes referred to as a big delta configuration. A motor connection diagram illustrating a 12-lead motor set up in the high voltage delta configuration might look something like this. Again, you'll note that the numerical arrangement of the terminals for a high voltage delta configuration is different than the other configurations, Y or delta. You note it goes 4, 5, 6 left to right this time. This prevents lines crossing each other in the diagram. Not all manufacturers use this technique, so be prepared for variations on this theme. While we've got these visualizations right in front of us, let me reiterate an earlier point. This is not art school, and you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise you might damage the motor, your equipment, or yourself. Windings and terminals are not equivalent and cannot be substituted one for another or hooked up backwards. For example, if we swapped winding 1-4 with 3-6 in a low voltage Y configuration, this would not work because winding 1-4 is intended for phase L1 with a phase shift of 0 degrees, whereas winding 3-6 is intended for phase L3 with a leading phase shift of positive 120 degrees. I must remind you that winding 1-4 and 3-6 occupy different physical locations around the circular perimeter of the stator, and nearby windings are dependent upon 1-4 and 3-6 of not only doing their job, but doing their job at exactly the right time. Improperly connected 1-4 would peak too early and 3-6 too late. The incorrect electrical connection of these windings would result in a hitch or an outright disruption of the rotating magnetic field. Similar cautions can be made against hooking windings in a reverse fashion since current direction influences magnetic polarity. Backward windings would be norths when they're supposed to be souths and vice versa. If you think about it, a single backwards winding in a circle of 11 properly connected windings is the one jerk that ruins the whole show for everybody. You know which lab partner I'm talking about, don't you? All right, that's about it for today. Before we go, a brief summary. Motor connection diagrams illustrate how to configure a motor as a Y or a delta, and whether they are or are not suitable for dual voltage operation. 3-lead Y configured motors and 3-lead delta configured motors are not customizable and are intended for single voltage operation. 6-lead motors are also intended for single voltage operation, however can be configured as Ys or deltas. This gives us 2 options: 6-lead motors configured as Ys or 6-lead motors configured as deltas. 9-lead Y configured motors and 9-lead delta configured motors are not customizable, however they can be used for dual voltage operation. This gives us 2 options each: 9-lead low voltage Ys, 9-lead high voltage Ys, 9-lead low voltage deltas, 9-lead high voltage deltas. 12-lead motors are fully customizable and can be used in dual voltage operation. A single 12-lead motor effectively gives us 4 options: 12-lead motors as low voltage Ys, 12-lead motors as high voltage Ys, 12-lead motors as low voltage deltas, and finally 12-lead motors as high voltage deltas. I should note there exist Y delta configurations, which as the name implies is a Y inside a delta. This is a barrel of monkeys I do not wish to open, but with a little bit of thought and imagination you could see how a 12-lead motor could be configured as such if you wanted to. Lastly, I should remind you that certain types of reduced voltage starters make use of different motor configurations to reduce inrush current and modify the starting torque of a motor under their direction. Y-start, delta run reduced voltage starters, as implied by their title, necessitate a motor that can be set up as a Y or a delta. This method can only be used for 6 or 12-lead motors. Part winding reduced voltage starters initially use one set of windings during the acceleration phase before the other set is brought in parallel. Only motors with parallel windings, i.e. low voltage configurations, can make use of this technique. This leaves 9-lead low voltage Ys, 9-lead low voltage deltas, 12-lead low voltage Ys, and 12-lead voltage deltas as available options. We'll examine these and other reduced voltage starting techniques like primary resistor reduced voltage starters and soft starters in later lectures. Finally, motor connection diagrams are not poems, songs, or paintings to be debated, interpreted, or modified. Follow the connection diagrams exactly as illustrated, otherwise you might damage the motor, your equipment, or yourself. In conclusion, this lecture discussed motor connection diagrams. We'll examine 3, 6, 9, and 12 lead motor connection diagrams and discuss dual voltage motors, Y and delta configurations, and briefly discussed how motor connection diagrams may influence the suitability of certain types of reduced voltage starters. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.